Classical Physics Tutoring Chapter 4 Section 2 Statistical Thermodynamics. Now, thermodynamics, we see some success in connecting Newton's basic law to the thermodynamics, especially in the ideal gas. So ideal gas, you have molecules flying around all kind of direction, and that's create pressure and energy related to the temperature we defined. Okay, so what happened is we defined the ideal gas and use Newton's kinetic energy as a source of energy. That means in ideal gas, the total energy is strictly kinetic energy, and potential energy and the thermal energy disappeared. Okay, and molecule flying around, the height is the same for every molecule, so no potential energy, no thermal energy, everything kinetic energy. And this attempt somewhat successful understanding the behavior of ideal gas. So it's called statistical thermodynamics. Thermodynamics. The reason why it's statistical is after we handle all the molecules flying around, we take average E, and that's going to give some kind of temperature, and also it's give the pressure. We can define the pressure using this. So statistical average is what we observe in the ideal gas. So we handle ideal gas is a bunch of flying molecules, and this method give insight for us to connect the micro world and micro world, and that's in that sense it's somewhat successful. But we cannot handle every thermodynamics science using Newton's kinetic energy equation. This has been successful only for ideal gas, but everything else, thermodynamics science stand itself. It's independent from Newton as a classical physics. Okay, so we have to define some common parameters used in thermodynamics. Gas mass is, you have gas contained, total weight is m. The weight of each molecule, like oxygen, the oxygen alloy is 16 grams. How many? It's 1 mole. Okay, we define the mole later. And the Avogadro number is this number, is called a mole. And when we talk about how much molecule we're talking about, 1 mole or 2 mole, so and so. Okay, so 1 mole is this many number of molecules. Okay, if you put oxygen this many together, it's 16 grams, but oxygen exists as a O2, so it's going to be 32 grams. So this is a molar mass. 1 mole of molecules, how heavy is it? That's molar mass. So in a sense it's the same, but this m is any kind of quantity. M is fixed quantity, Avogadro number times the weight of each molecule. Okay, the number of mole, N, is how many moles. So if molar mass is m, obviously the weight of gas is n m, depend on how many moles in the container. Okay, gas constant is actually the energy per mole in the 1 mole of gas, how much energy is contained inside. Okay, and that's times the depend on the molecule. Total energy is going to change. Total energy is E. Okay. Boltzmann's constant is the energy contained in each molecule per temperature. So at a certain temperature, the how much energy per molecule. This is a microworld constant, Boltzmann constant. Okay, so K over mu is R over M. So you look at the definition above. So that's what the Boltzmann's constant is. Now, the assumption spelling error. Assumption here is, say the gas is Vx, Vy, Vz. It's flying around everywhere, right? And every direction. So we divide into 3 directions. And if you look at the distribution of Vy, it's probably like this. And this is average Vy. And average Vx here the same way. Okay, why we can assume that? The reason is, number 1 is totally random. Okay, number 2, equilibrium. So molecules flying around, occasionally it's collide and they reach equilibrium state over the long time. Okay, and it starts with a totally random set of flying molecule. So once it's reached equilibrium, that's what we are interested in. So we assume this, then it turned out to be a Gaussian distribution. It's a probability. You learn the Gaussian distribution. If you throw the coin 1, 0, totally random event, repeat many times and take a statistic, it's become a Gaussian distribution. It's the same thing you see here. It's the nature of this kind of model. Okay, suppose total distribution is a 3D is Pxv, Pyv, Vz is total independent on each direction. So V is the vector length. This is the distribution probability of velocity. What kind of speed the molecule is, you make a probability function. That's the function here, and we take a the partial derivative on the Vx. So we don't care about Vy, Vz because it's independent, right? And divide by P over V. Then we will get this equation. Okay, and Vx over V is V prime here. So you substitute that and you look at the equation and say, this guy is nothing to do with Vx, Vy, independent, right? So actually we can assume even the distribution of Vx, Vy, Vz is the same as this. So we can say pretty much this is constant. Okay, so we introduce the constant value -2 beta, convenient. We can get log PV, derivative is -2 Vx. So as a result, PV is, we get A exponential minus beta Vx square. So this is a Gaussian distribution. Okay, so this Gaussian distribution, we have to determine the A. And how do you take if you take an integral of entire range, it should be 1, right? Probability theory, remember? And how you take a integral of this kind of function. I made another video how to integral challenge. You should look at this. So using that result, the constant becomes square root of beta over pi. Okay, so we are getting close. We determined the constant, we got the distribution of the velocity, and energy. Energy is 1/2, and molecule weight and v square, right? So the energy on the x direction is going to be Vx square Px Vx dVx, and you add up all the particles in this distribution. So it's turned out to be 4 beta. And this is very simple. And if you do for Vy and Vz, you have a 3 degree of freedom. You have to multiply that many. Okay, so now beta becomes 2kt. Okay, now energy actually for all the direction total is 3kt/2. This energy equation, using this, the distribution of velocity is going to be 2 pi kt, 3 degree of freedom, right? Exponent minus e over kt. Looks familiar. What is e? V square. Okay, so this is the distribution function of the molecule freely flying around in the ideal gas. Okay, and now we take how many molecules at the V. We take V plus delta V to be this range. This is, distribution is like a symmetric sphere distribution. So we take 4 pi v square dv, right? So the molecules, number of molecules at the V is going to be 4 pi and this guy, and v square exponent minus e over kt, and it's turned out to be we can take a derivative by dv to find out the the peak maximum. Okay, so that's actually what it is. Using this distribution, we can get the average, we can get the energy and average speed and all the statistics. So how we relate that to the ideal gas that we observe? Okay, we have so-called Dalton, not Dalton's, Avogadro law. That means PV over T is constant. And what we know is you have volume and pressure, and consider the work performed when you enlarge the volume, delta V. Force is P. So PV imply the work, right, equals energy. So energy over T is constant. Okay, so we have that from the distribution E equals 3 over 2 gas constant T. So energy over T is constant. This R is Avogadro numbers times mu, right? So now what Avogadro law is saying is PV over T is constant in ideal gas, which exactly match up with the result of this statistical thermodynamics model. So what we do is we use that. We take a gas, and the gas, we introduce the coefficient. So when you change the volume, and the pressure change, then temperature change as a result. Depend on how much volume, depend on how much pressure change. This is Avogadro's law. Okay, using this Avogadro's law, we measure the temperature, and this temperature match up very well with this definition, the result from the statistical model. So we have something here. This statistical model is pretty accurate for ideal gas. Okay, so experimentally we defined T using different molecules. We do experiment and plotted the T. The T is defined by this. So from statistical thermodynamics viewpoint, we defined temperature by this equation: energy 3 over 2 RT. Okay. Now Dalton's law. Dalton's law is something like you have a volume V of gas 1 and volume V of gas 2, pressure 2. We put them all together into the same volume. What will be the final pressure? It turned out to be P1 plus P2 plus so-and-so. It's going to be final pressure P. Okay, so the proof is here. You can look at. It's not that difficult proof. This is called Dalton's law. So ideal gas, there are several others law you can derive using the basic equation. And one of the interesting things is van der Waals equation. What is van der Waals equation? Well, it's deal with change of pressure. And actually, there is the molecules has attractive force. This force has an effect on the pressure. So the pressure, actual pressure, include this force. This is van der Waals coefficient. And the volume, actual volume, is actually, we need to exclude, because when it's get high pressure and crowded, the molecule occupies certain space out of the pressure. So the volume has to be slightly less. That's another van der Waals constant. And that's a kind of adjustment. And when this kind of constant comes into the play at the low temperature, right? When the temperature is low, you start seeing van der Waals effect. And this is the temperature, and you draw the curve. PV is constant, right? But it starts deviating slightly here when temperature goes low. And very interesting phenomena is occasionally there is an inverted relationship between P and V at the low temperature. So that's a kind of the non-ideal gas. Non-ideal gas. So the model has to be modified. Okay. So that's all about the statistical thermodynamics today, and I hope you enjoyed this video. If you like, subscribe.